All right, so we are reviewing sequences and series. So to start off, sequences are essentially a list of numbers. It's an ordered list of numbers. We put it in the little curly brackets to say that it is a sequence. And a sub n is what's called the general term. So usually that's going to be some function with n's in there. And we have that a sequence is convergent if the limit as n goes to infinity of our general term is equal to L, which is some finite number. If you get infinity or negative infinity or dne, that would be divergent. All right, so some examples. We have natural log of n over n squared. If you take the limit of this as n goes to infinity and apply Calc 1, you'll get that this limit goes to 0. So the sequence converges to 0. Anytime we're talking about convergence of a sequence, we're just talking about where does the sequence go, and it's the same idea as limits at infinity from Calc 1. And then this sequence, if you take the limit as n goes to infinity, you find out that this sequence ends up going to -2. So we say that this sequence converges to -2. Now, like I said, you can evaluate these limits using Calc 1. Just keep in mind that what you're doing when you're using Calc 1 is you're considering the function, the continuous function that our sequence lies on. So we have this function, which is continuous. We can evaluate the limit as x goes to infinity. It's at least continuous as x goes to infinity. And our sequence happens to lie right on this function. So whatever happens to this function, if this function has a limit, then our sequence has a limit. If this function blows up to infinity, then our sequence blows up to infinity. If the limit of our function does not exist and it oscillates, our sequence is going to also oscillate. So that's what we're looking at. All right, so we have a squeeze theorem for sequences. So we have if a sub n is less than or equal to b sub n is less than or equal to c sub n. So we have this inequality. And we know that a sub n converges and c sub n converges to the same number. Then since b sub n is squeezed right in the middle, b sub n must also converge to that same number. And I'm realizing I have a typo. So we can make a conclusion about b sub n. So we have this example. Determine if the sequence converges. We have sine of n over n. And so we can use squeeze theorem on this sequence just like you would have used squeeze theorem on a function like this in Calc 1. So we're going to try to bound the sequence between two things that we know converge and that they converge to the same number. They have the same limit. So we can use the fact that sine of n, no matter what I plug in for n, this is always going to be bounded between -1 and 1, which means sine of n over n is always going to be bounded between -1 over n and 1 over n. Well, if I evaluate the limit as n goes to infinity of -1 over n or +1 over n, both of these come out to 0. Well, since I have that this sequence lies between these other two sequences that do converge, my sequence sine of n over n must also converge. So we could say by squeeze theorem, the limit as n goes to infinity of sine of n divided by n is equal to 0. And this is how you would set up the problem. So we have our justification here. We're stating that we're using this theorem, and then we have this conclusion. All right. Next, we have the monotone convergence theorem, which says that any sequence which is bounded and monotone is convergent. And so in class, we went over a little bit more detailed as to why this is true. I'm just going to kind of draw some pictures. So let's say we have a sequence. The first one I draw is going to be in green. And let's say my sequence starts here. And let's say it's monotone increasing. That means that every subsequent term of my sequence is going to be greater than or equal to the previous term. So essentially, if it's monotone increasing, I can either stay at the same number or I can go up. So let's say I stay at the same number. I could stay at the same number for all time. And if I'm staying at the same number for all time, then my sequence has a limit. It's going to be whatever number I'm staying at. If I continue to increase, well, and I'm bounded above, and I can't pass this line for big M, we essentially have like a horizontal asymptote from Calc 1 and pre-calculus, essentially. And we end up having a limit there. So it forces us to have a limit. If we have a monotone decreasing function, let's say I start here, basically we're playing the same game but upside down. So if I'm monotone decreasing, I can only go down. And I can either go down all the way to little m, and then I have to stay there because I'm bounded below by little m. Or I could level off somewhere between little m and big M, but I'm bounded there, and I essentially don't have anywhere else to go, and I can't wobble around. So that's the monotone convergence theorem. And then we had series. Series are infinite sums. So we have this notation. This means the sum. K equals 1 to infinity is letting us know we're going to start our indexing at 1, and we're going to have an infinite sum. So if I were to write this out, we'd have a sub 1 plus a sub 2 plus a sub 3 plus, and we'd just keep going. We'd get a sub n for any integer n, and we'd just keep going. N goes to infinity. And one problem that we have is trying to figure out, does this sum approach a number? Does this sum have a sum that is finite? And so what we do is we look at the sequence of partial sums. So essentially I'm going to add up the first term. I'll call that S1. So S1 would be A1. S2 would be A1 plus A2. S3 would be A1 plus A2 plus A3. And essentially what we're trying to do is figure out, does that sum level off anywhere? Is what essentially we're trying to figure out. Does it level off? Does it approach a number? And so we look at the sequence of partial sums. So we have that the series is equal to, if I look at these partial sums, so I'm summing up finitely many of these, the number is n, and I'm allowing n to go to infinity. Well, this right here are our partial sums. So what we're really looking at is the limit as n goes to infinity of the sequence of partial sums. Okay. Notice that pulling this infinity out is very similar with what we did with improper integrals. All right, so we have this series here, and we want to figure out if this converges. So determine if the series converges. Might be the instructions. And so all that we have so far, because let's assume we haven't learned any of the tests yet, all we have so far is, well, is this sum leveling off anywhere? And so what we can do is look at the sequence of partial sums. So the first term is going to be 1 over 1 times 2, so 2. When I add up the first two terms, that's the second partial sum, I'll have 1/2 plus 1 over 2 times 3, which is 6. And I can combine terms here. I end up getting over 6, 3 4/6, so 2/3. And then we can look at S3. So we'll take that 1/2 plus 1/6, which is 2/3, plus 1 over 3 times 4, so 12. And we get this is equal to 8 plus 1, so 9 over 12, or 3/4. And we can keep adding up these partial sums and notice a pattern. And that's the first kind of thing that we talked about with determining sums of series, is see if you can find a pattern with their partial sums. See if you can find the limit of their partial sums. Well, this one, notice that there's a pattern to where S sub n is going to be equal to n divided by n plus 1. Notice this is this 1/2 is 1 over 1 plus 1. This is 2 over 2 plus 1. This one's 3 over 3 plus 1. There's this pattern that we've established. You could do S4 and S5 and double check that it's working. And so essentially, if I add up the first n terms, so if we add up n terms, our partial sum is this S sub n, n over n plus 1. Well, when we're looking at our series, I'll use a different index. Let's say k equals 1 to infinity of 1 over k plus 1. When we're looking at our series, what we want to know is if I add up infinitely many of these terms, what is this sum? Well, that's if I take limit as n goes to infinity of whatever my sums are at n, right? So I'm taking the limit as n goes to infinity of my partial sums. And we evaluate this and get 1. Since I got that the limit of my partial sums is a number that is finite, that is equal to the sum of my series. So notice these two things are equal. So our series converges. To 1. All right, next example. We talked about telescoping series. So these ones are series that are really, really nicely set up to where when you look at the partial sums, they have some really nice cancellation. So let's go ahead and start looking at the sequence of partial sums. So if I look at S sub 1, this is going to be e to the 1 over 1 minus e to the 1 over 1 plus 1, so 1/2. No cancellation yet. If I look at S2, I'll take my e to the 1 minus e to the 1/2, and I'll add to it e to the 1/2 minus e to the 1/3. Well, here we have some cancellation, this e to the 1/2. But let's keep going and make sure that that's happening throughout. So if I look at S3, I'd end up getting e to the 1 minus e to the 1/2 plus e to the 1/2 minus e to the 1/3. Oops. Plus e to the 1/3 minus e to the 1/4. And here we've established this pattern that we're going to get some nice cancellation between terms. So if I look at S sub n, I'm going to have e to the 1 minus e to the 1/2 plus e to the 1/2 minus e to the 1/3. And I'll keep going until eventually I add e to the 1 over n minus e to the 1 over n plus 1. And notice that the cancellation that's been happening is that this tail of the previous term cancels with the front of the next term, and then my tail cancels with the front. Eventually, this e to the 1 over n is going to cancel with the previous term as well, and we end up getting that this S sub n can be rewritten as e to the 1 minus e to the 1 over n plus 1. Well, we're just going to look at the limit as n goes to infinity of these partial sums. So limit as n goes to infinity, e to the 1 minus e to the 1 over n plus 1. This is giving me e to the 1, which is just e, minus e to the 0, or 1. And that is going to be the sum of our series. So we have the series converges. To e minus 1. All right, next we talked about the geometric series. And we did a whole proof in class. We're not going to do the proof on this video, but we got this formula essentially for the geometric series. We have it completely figured out. So for the geometric series, so long as my indexing is starting at 0, we have this nice formula that we derived in class. So long as the absolute value of my common ratio, r, is less than 1, then my geometric series is convergent, and its sum is going to be a over 1 minus r. And so we can plug into this formula anytime we want. Just make sure that n is starting at 0, because this formula, the way it's written, is set up exactly for n equals 0. And then if r is greater than or equal to 1, then the series is divergent. So anytime you have a series and it's a geometric series, you find your r. If the absolute value is greater than or equal to 1, you can say it's divergent. If it's less than 1, then you can plug into this formula. All right, so suppose we have this as an example. Notice that I have numbers raised to nth powers. This is what's telling me it looks like I have a geometric series. I just have to rearrange a little bit. And if I'm thinking ahead, assuming that I'm going to want to use that formula, I see that my n starts at 3. So the first thing that I would suggest you do is shift this index so that you actually start n equals 0. And so you'll shift here, and then you'll shift anywhere where you have an appearance of n. You want to make sure that you have the same terms. So let's shift it. I'm going to start at 0 instead of 3. Well, the first term up top, notice that when n started at 3, my negative 3 started at 3 minus 3, so it started at 0. So I want to make sure that in my new sum that I'm writing, that my negative 3 is going to start with an exponent of 0. Well, that's just n. So we're good to go there. And then I have the 1/2. In the previous series, when n started at 3, this exponent would have been a 3. I want to make sure that this exponent starts at 3. Well, since I'm starting n at 0, I can take n plus 3, and then I'm guaranteed to start where I'm supposed to start. And then when you're adding integers, everything else is going to follow really nicely. So now we've fixed our index. Well, now we just want to rewrite this so that we have the form a times r to the n. So we can use properties of exponents to rearrange. So I've got negative 3 to the n. I can pull out a 1/2 cubed and be left with 1/2 to the n. And then finally, I can smush the negative 3 and 1/2 to the n. And then this 1/2 cubed gives me a 1/8. So we have 1/8 times negative 3 over 2 to the n. Now, this series has an r, which is negative 3 over 2. Well, the absolute value of r is greater than or equal to 1, which means the series is divergent. And we can say it's divergent by geometric series. Now, I want to show you how this work could be used if we had a convergent series. So let's suppose, I'm going to make some edits now, so it's not going to be the same problem. Let's suppose instead of a 2, I had a 1 over 4 to the n. We would run through the exact same rearrangements, but anywhere I had a 2, that would become a 4. So I'd have 4, 4, 4. And then we'd have a 64 here. And now we would have R as this negative 3/4, which is less than 1. The absolute value is less than 1. So our series converges. And we can actually find the sum. To find the sum, we would just use our formula, and we're good to go to use our formula since n starts at 0, where we have a, 1 over 64, divided by 1 minus r, so we get 1 plus 3/4 because the 3/4 is negative. And we end up getting 1 over 64 times, we can do the reciprocal of 1 plus 3 over 4, which is going to give us a 4 over 7. So we end up getting a 1 over 16 times 7, which gives us a 1 over 112. That's going to be the sum of this geometric series. All right. Well, many series, we can't actually find the sum very easily or at all. But we still might want to see if it converges. So we have some different tests that let us know if the series converges or diverges. They don't find the sum of the series, but they determine if the sum exists. So the first one is the divergence test. You cannot conclude anything about convergence, like if the series converges from the divergence test. It's just saying if the limit of the terms in our series are not going to 0, then we can say that the sum diverges. We have integral test, which essentially would take our a sub n's and compare them to f of n. If f of n is continuous and decreasing, we're good to go with using integral test. You're going to set up the integral from some starting point. This just has to be a finite number. So it could, commonly you'll start at 1 or 2, but you could start at 100 if you wanted to. We really care that as we go to infinity, does the tail of this integral, so the tail of the area under the curve, if that tail converges or diverges. Whatever happens to this integral, so long as you can compute this integral, whatever happens to the integral happens to the series. So if the integral converges, you get a finite number out, then the series converges. If the integral diverges, then the series diverges. The problems are just that you need to be able to evaluate this integral, and f needs to be a decreasing function. All right, then we have the comparison test. If we take the terms of our series and we can bound them below by 0 and bound them above by terms of another series that we know converges, then we can say that the series with a sub n converges. We can also bound a sub n below by a series, terms of a series that we know diverge. They have to be greater than or equal to 0. But if we know that these guys diverge, then we're good to go with saying that the series with a sub n diverges with comparison test. We have limit comparison test, where we look at the limit as n goes to infinity of our original terms, our a sub n, divided by terms of a series that we know if it converges or diverges. So when we evaluate this limit, we could get some number which is non-zero and we can make a conclusion. We could get 0 and make a conclusion. We can get infinity and make a conclusion. But it relies on us evaluating that limit, and we have to know if b sub n converges or diverges. We have the alternating series test, which if we have an alternating series, which specifically can be written as -1 to the n, This could also be an n plus 1. It doesn't matter for the test. We have an alternating series where these b sub n's, when we ignore the sign, decrease to 0. So that means that a b sub n plus 1 is got to be less than or equal to b sub n. And the limit, as n goes to infinity, of b sub n is equal to 0. Those two conditions combined say that our b sub n's decrease to 0. If that's true, we have that these are convergent. If you can't show those two things, you can't make a conclusion and you have to move on to another test. We have a ratio test, which tells us to look at the absolute value of the ratio of consecutive terms. If the limit as n goes to infinity of the absolute value of these consecutive terms goes to a number less than 1, we have that it converges. If it's greater than 1, we have that it diverges. If it's equal to 1, this is our inconclusive case, and you have to pick a different test. For root test, very, very similar to ratio test, except this time we're taking the nth root of the absolute value of our terms. If we can evaluate this limit and we get something greater than 1, our series is going to diverge. If it's less than 1, our series is going to converge. If it's equal to 1, then the test is inconclusive and you have to pick something else. All right, so we have some different examples. I would suggest that you pause the video before watching my explanations. With some of these, if you don't see the test to use right away, you're going to have to start applying some, and if they fail, then you pick a different test. And if it works out, then it works out, and that's great. I think that the test for divergence tends to be a pretty quick check. And so I would suggest, even if you don't write it down in your head, check if the limit of your terms, if these go to 0, then proceed with another test. If they don't go to 0, test for divergence concludes that your series is going to be divergent. And for this one, it does. So we can say limit as n goes to infinity of our a sub n, so 2n plus 1 over n plus 2 is equal to 2, which is not equal to 0. So the series diverges by a divergence test, or test for divergence, however you want to phrase that. And that, we're done. We've concluded that the series diverges. All right, we have this next one. Again, pause the video if you want to try it first. So, we could look at, for this one, natural log of n divided by n to the 5th. And we can actually bound this bound it below by 0 for any n that's greater than or equal to 1. And this we can bound above by n over n to the 5th for any n that's greater than or equal to 1. You can think of the graphs of these functions. Natural log of x looks like this. X just looks like this. X is always going to be over top of natural log of n. If you want even further reasoning, what I'm saying is natural log of n is going to be less than or equal to n. Well, if I take both sides and do e to each of these sides, we get n is less than or equal to e to the n. And for sure this is true when I'm talking about n greater than or equal to 1. So we're good with this inequality. And this is set up perfectly for comparison test. So notice on the right-hand side, this is just 1 over n to the 4th, which those are the terms of a convergent p-series. So once we set up this inequality, we can say since, and we have the series n equals 1 to infinity of 1 over n to the fourth is a convergent series. We can mention that it's a p-series. The series from 1 to infinity and natural log of n over n to the fifth is convergent by comparison test. So we compare the series terms, and then we can make a conclusion about the series. All right, next one, we have the series from 1 to infinity of n to the n over 3 to the n. This one lends itself really well to root test. Root test helps when you have nth roots. Essentially, you get a bunch of cancellation with that, and then hopefully what you get is something that you can evaluate the limit well with. So we can look at limit as n goes to infinity of the nth root of the absolute value. These are all positive, so you don't have to write the absolute value here. But technically it is the absolute value of n to the n over 3 to the n. And we're going to roll through and try to evaluate this limit. So we've got limit n goes to infinity. When I take the nth root of the numerator, I get n. When I take the nth root of the denominator, I get 3. When I evaluate this limit, I get infinity, which is greater than 1. So the series is divergent by root test. Okay, so we have our work for root test, and then we have our conclusion about the series, and we mention the theorem that we used. All right, another problem. We have the series from 1 to infinity of n factorial over n to the n. And we're going to kind of play around with this one. So we see a factorial. Maybe we try ratio test. So we're just setting up ratio test. And we get a little bit of cancellation. So we've got n plus 1 times n to the n plus 1 to the n plus 1. We get some more cancellation with the n plus 1s. So we get n to the n over n plus 1 to the n. Well, if you take the limit as n goes to infinity of this and consider what would end up being the leading terms, this is 1. So ratio test is inconclusive. So we have to try another test. If you're on an exam or a quiz, I wouldn't suggest scratching this out completely. Just say ratio test is inconclusive. If you continue doing other tests and you appropriately find tests that are inconclusive, that at least gets you some partial credit. It shows that you understand how to apply the tests and that you actually understand the conclusions of the tests. So next one, we could try maybe root test. So we look limit, n goes to infinity, nth root of n factorial over n to the n. And we're evaluating this limit. And this nth root of n factorial gives us some trouble. And so this kind of leaves us a little bit like, we've never evaluated a limit where we have a factorial in there. certainly not in Calc 1. And so we're kind of stuck here on evaluating what this is. It looks like we have maybe infinity over infinity, maybe 0 over infinity, maybe 1 over infinity. We're not quite sure. The n factorial is tripping us up. So we can abort ship here and try another test. I would suggest looking at what n factorial over n to the n is meaning. And I would suggest you pause the video right here, see if you can play around with this and figure out what other test you could use. Okay, so when we write out what this is equal to, we have a 1 over n times 2 over n times 3 over n all the way up to n over n. If we stack the factors of our numerator and the factors of our denominator really nicely. And so we can think, do I want to show that this converges? Do I think it converges? In which case I want to bound it above by something that is convergent if we're thinking of using comparison test. Or do I think it diverges? In which case I want to bound it below by something that diverges. And thinking about what's going on with the n factorial and the n to the n, I would think that maybe it converges. So at this point we can think maybe it converges. And so we can try to bound it above by something that converges. And so we can try that. So notice, if I look at these first two terms, I have 1 times 2, so 2 over n squared. If I'm just considering that, that gives me a p-series. Well, the rest of these, each of these terms is less than or equal to 1, which means when I multiply by each of those terms, it's taking whatever I had and it's making it smaller, which means if I get rid of those terms, I should have something bigger. So if I get rid of those terms and just consider 2 over n squared, that's going to be larger than whatever n factorial over n to the n was. And right here, we have something perfect for comparison test because also, for sure, n is a positive integer. That is bounded below by 0. So we can actually use comparison test. So we have 0 is less than or equal to n factorial over n to the n is less than or equal to 2 over n squared. Since 1 over n squared converges by p-series the sum from 1 to infinity of 2 over n squared converges, and hence the series n factorial over n to the n converges by convergence test. Okay, so we have that one. Now, there's one more thing with series that I did not mention up here originally with these different things we can use. And it is absolute convergence. So if you look at your series with absolute value over everything, if this converges, then that implies that your original series converges. And then the series a sub n is called absolutely convergent. And this comes in handy when we're looking at series where if we didn't have an issue with the signs changing back and forth, if we could, let's ignore alternating series tests. Let's maybe think about something like, here's another example. Let's think about something like cosine of n over n cubed, something like this. Well, cosine of n is tricky because cosine of n, it has positive and negative values. So it's we have cosine of n is bounded between -1 and 1. But this doesn't exactly give us, it doesn't give us an alternating series. We're not switching back and forth between -1 and +1 and -1 and +1. We have negative numbers and positive numbers, and we might have multiple in a row. We're not flipping back and forth perfectly from positive to negative to positive to negative. And so we can't use, this is not an alternating series. And so what we could do is we could try to use comparison test on this, to where we have cosine of n bounded between -1 and 1. And so this is our inequality with all of our terms. But we don't have this bounded below by 0. We need, for comparison test, for this to be bounded below by 0. Otherwise, we could have our sum wobbling around if we have negative terms and that it never actually converges, which is why we need to bound it below by 0. Well, if we consider absolute value of cosine of n over n cubed, then we know that this is bounded below by 0. And now we can apply comparison test and say that cosine of n over n cubed is convergent by comparison test. So we have the series n equals 1 to infinity of cosine of n over n cubed is absolutely convergent. So not only is it convergent, it's stronger than just convergence. It's absolutely convergent, which means the terms when you take the absolute value and look at that series that it's convergent. And so you can use this to simplify problems if basically the thing that's tripping you up is the fact that you're getting negative numbers. So that is also helpful for these types of problems.